recording and then we will get on the road. All right. So we left off talking about how we can organize the periodic table into thinking about where that last electron goes and how it's an S, P, D, or F, whether it falls in the S, P, D, or F blocks, and also how we can figure out the electron configuration based on just the position of an element, right? Again, each period is represented by a principal quantum number n. And so if n equals 1, right, we're in period 1 with the 1s. Period 2, n equals 2, we have the 2s and the 2p. For period 3, n equals 3, we have the 3s, the 3p. And then comes the 3d. Now remember that in multi-electron elements that the 3d subshell is higher in energy than the 4s subshell. And so we put it later in the periodic table. And so instead of sitting in period 3, it actually sits down in period 4. The F blocks are shifted down by 2 periods. And so when n equals 6, we have the 4F subshell, and when n equals 7, we have the 5F subshell. Okay, so let's take a look at this last example from chapter 7, and then we'll get into chapter 8. The ground state electron configurations for sulfur and palladium. Now that we have the periodic table, we're going to use it, right? So here's sulfur. He's in the n equals 1, 2, 3, and this is the p block, and he has 1, 2, 3, 4 p electrons. And so we know that his 1s2 has to be full, his 2s subshell has to be full, his 2p subshell has to be full, his 3s subshell has to be full, and his 3p subshell has just 4 electrons in it. Okay. We can double check. Sulfur has 16 electrons, and so we could add that up. 2, 4, 6 is 10, 2 and 4 is 16. That's another way to double check ourselves. For palladium, he's in a D block, and he's in n equals 5. So that means that he's in the 4D, and he has 1, 2, 3, 4, 5, 6, 7, 8 electrons. But it gives us a little hint here. Palladium is diamagnetic. Diamagnetic means that everything's paired, or that we have some unpaired left over?
Everything is paired.
Yeah, diamagnetic means everything's paired up. So, well, we're going to start the 1s, 1s2, 2s2, 2p6, 3s2, 3p6. Next comes the 4s, 4s is full. Next comes the 3d, 3d is full. Next comes the 4p, 4p6, 5s2, and then 4d8. Now, it's hard for us to tell based on just the electron configuration whether or not palladium's diamagnetic. So I'm just going to draw out the noble gas electron configuration. If we're talking about palladium, his noble gas is, let's see, krypton. Krypton, 5s2, 5s, 4d, 1 orbital in the 5s, 5 orbitals in the 4d, 1, 2, 3, 4, 5, 6, 7, 8, 9. Remember, we spread them out due to Hund's rule. Hund's rule tells us we're going to spread out all the electrons with their spin up before we start to pair them. Right? So if it were 5s248, palladium would not be diamagnetic, right? And so in order for us to make it diamagnetic, we can't break Hund's rule, right? We can't pull those two 4d electrons and put them in the same orbital. What we can do, and this Aufbau principle, remember, is the building up principle as we start at the lowest energy. The 5D, the 5S and the 4D are very close together in energy, right? So 5S is a little lower than the 4D. What happens is, as we add in electrons, the energy levels come down a little bit. And it turns out that as we load in more and more electrons into that 4D subshell, the energy of that subshell at some point gets lower than the energy of the 5S. And so those 5S electrons decide they're going to move down so that they're in the lowest possible energy arrangement. And so we actually move these two electrons into the 4D. We end up with 4D10 and no 5S. So I'm going to strike out this last bit here. 4p6, then 4d10, no 5s electrons. Now, the only reason we knew to do that was because it told us that palladium was diamagnetic, right? And so if it tells you something like that, again, just keep in mind that Hund's rule is a very strict rule, and that we can't leave an orbital empty if we have enough electrons to give it at least one, to give all the orbitals at least one. But because the energy levels shift around a little bit as we load in electrons, it's likely that those 5s electrons are going to go over into the 4D. We'll talk about that a little bit more as we jump into chapter 8, but that's the tail end of chapter 7. Any questions on how to write these electron configurations? Looking at a periodic table, being able to come up with an electron configuration. All right, hearing none, I'm going to move on. This is chapter 8. The chapter 8 slides are up on Moodle. If you haven't already downloaded those, you should go ahead and do that. This is an interesting little diagram, another way of arranging the elements. Chapter 8 talks about how the relationships between elements is that periodic relationship, right? We call it the periodic table because every once in a while we come across an element with a similar set of properties. And so if we look here, we've got lithium, sodium, potassium, rubidium, cesium, francium, and element 119. These are all our alkali metals, right? If we keep going around this wheel, there's our alkaline earths, group 2. Here we got group 3, group 4, group 5, group 6. And then here we have our noble gases, group 8. So the groups have similar properties. We call them periodic relationships because if you go down a period, you'll see that the elements match in the properties of those elements above and below it. Okay. All right, so jumping into it, one of the first things that we know and should be obvious to us after we talked about electron configurations in chapter 7 is that the electron configuration for the elements does vary by group. And so what's the electron configuration for hydrogen? It's real easy.
1s.
1s with how many electrons?
1s1.
1s1, absolutely. What's the lithium configuration?
1s2, 2s1.
That's it, 1s2, 2s1. And so for this whole group here, okay, this whole group ends with whatever period they're in, S1, right? So the principal quantum number for whatever period they're in, S1. So hydrogen, 1s1, lithium, 2s1, sodium, 3s1, potassium, 4s1, right? That's the last bit of their electron configuration. This whole group ends within S2, right? Again, the number of the period that they're in with two electrons in the s subshell. Now remember, helium belongs in this box, really. We put him over here because he's got a full subshell, so he behaves like the noble gases, but in terms of electron configuration, he doesn't really belong there. I'm going to jump over the transition metals just for a minute. If we go to this column, what do all of those elements end with?
S2.
Yeah, they have NS2, and then what else?
Oh, I was.
P3.
Yeah, P3.
Yeah.
Okay. So they all end with NS2 and NP3. The noble gas, the transition metals are the same, right? If we chose this group, for example, it'd be NS2 and then N minus 1 D3, right? Remember that the D block is all shifted by 1. And so if we were in period 5, for example, we were looking at niobium, NB, it would be 5s2, but then 4d3.
I have a question for you, Dr. Davis.
Yes, sir.
So on Alex, it was saying something like when we were doing electron configuration, it was having us put the like the S squared or S2 at the end, because it was saying something like if for example, I guess it would be like D3 and then like NS2. And it was saying it was because like the D was not, like, I guess, filled or something, so you wanted to end it with something that was like filled, but I didn't really get that too much.
Yeah, so this is one of those things that some textbooks do it one way, some do it others. Our textbook does it where the highest energy orbital is last. Apparently Alex does it where we sort of keep all the threes together. So for niobium, for example, it would be maybe 4s2, sorry, let's see, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d3, 5s2. That's what you're talking about?
Yes, sir.
Yeah. So they are keeping they're keeping the shells together, which is, like I said, another common way of doing it. And in my mind, one's not better or worse than the other. One thing that we haven't quite gotten to yet is this step differentiation between valence electrons and core electrons. Valence electrons are always electrons in the highest shell. Right? It doesn't have nothing to do with subshell. It's just the highest shell. And so
Yes, sir.
if you do write your electron configurations this way, it's always easy to see what the highest shell is, because it's always the last thing that you write. And so we would call these the valence electrons, and everything before that, including the 4d, which is not quite full, we call the core electrons, or sometimes the inner electrons. But the 4d electrons are considered core electrons, even though the 4d subshell isn't full. And so that's one argument for writing it this way.
Oh, that makes actually a lot of sense. Thank you very much.
Sure. And so the first thing that we can see is that this valence configuration, now that we've brought up that term, this valence electron configuration is going to be the same for all the elements that are in a particular group. Okay. All right. So if we have an atom with 15 electrons, without looking at the periodic table, right, we should be able to do this, figure out the ground state electron configuration of the element. Well, 15 electrons, we know, we can just add up. 1s2, 2s2, 2p6, that's 10. 3s2, that's 12. I've just got 3 more, 3p3. remember, for an element to be diamagnetic, that subshell has to be filled, right? Are all of the subshells in this element filled?
No.
No, right? And so it must be paramagnetic. If we really wanted to write it out, we could. 1s, 2s, 2p, 3s, 3p, up and down and up and down and up, up, down, down, down. That's 10, 11, 12, 13, 14, 15. Right? So we're paramagnetic with 3 unpaired electrons. But again, we knew that because the p subshell wasn't filled. Okay. All right. So now we're going to shift gears a little bit and talk about not atoms in their ground state, but atoms as we add or remove electrons to make ions, right? So now that we're adding and removing electrons, we have to think about how that changes the electron configuration. Okay. It turns out that atoms will lose or gain electrons in order to have a noble gas-like configuration. Remember, we talked a little bit on Friday about how that noble gas, excuse me, that noble gas configuration is very stable, right? All the subshells are full. It doesn't want to react anymore after it has all of those electrons. And so atoms are either going to gain or lose, and we know whether they're going to gain or lose based on their position in the periodic table. Right? If they, in other words, if they have to lose fewer than gain, then they're going to lose. If they have to gain fewer than lose, they're going to gain. So let's take a look. Sodium is neon. There's that noble gas, 3s1. So sodium only has 1 valence electron, right? That S is the valence electron. And so it's much easier to lose that valence electron than to gain 7 more electrons, right? Because he would have to fill up the 3s, which is 1 more electron, and fill up all the 3p, which is 6 more electrons, in order to have the same noble gas configuration as argon. If we take a look at calcium, right? Calcium is argon 4s2. He's got 2 valence electrons. And he could either lose 2 and become just like argon, but in order to become like krypton, the next noble gas, he'd have to gain 16 electrons, right? Not only the 6 from the 4p subshell, but also all 10 of those electrons from the 3d subshell. Right? And so he'd have to be a negative 16 charge in order to be like krypton, or he can just be a +2 charge and be like argon. And so for cations, remember cations are positively charged, lose electrons to become, or to reach that noble gas status, that noble gas configuration. If we take a look at what we know already to be negatively charged things like oxygen, right? Oxygen is helium, 2s2, 2p4. Oxygen only has to gain 2 electrons to become like neon, or he could lose 6 electrons and become like helium. It's easier for him to gain 2 electrons than to lose 6. If we took a look at phosphorus, right? Phosphorus is neon, 3s2, 3p3. Five valence electrons. Is it easier for him to gain 3 or lose 5? Well, it turns out it's easier for him to gain 3. And so all of our anions, they gain the number of electrons that it takes to reach their noble gas configuration. And so that's why in chapter 2, and we talked about how we know that sodium's always +1, calcium's always +2, oxygen's always -2, the halogens are always -1. The reason we know that is because they gain or lose the number of electrons required to get them to that noble gas configuration. And because the periodic nature of those properties, that particular group always gains or loses the same number of electrons. All right. Another topic that we've brushed on, but it's good for us to take another look at it, is this idea of isoelectronic species, right? Iso is our prefix for the same. And so isoelectronic means that they have the same electron configuration. Now, obviously, this isn't going to be true for just atoms, because each atom in its neutral state has a different number of electrons, and so can't be isoelectronic with anything else. But if we choose a noble gas, for example, I'm going to do neon. Neon is isoelectronic with a lot of different ions, because a lot of ions want to have a noble gas configuration, and neon is a noble gas. The elements that have that are isoelectronic with neon would be sodium plus, magnesium 2 plus, fluorine minus, oxygen 2 minus. Right? All of these species, all these chemical species, have the same number of electrons. Right? They all have 10 electrons. Magnesium had to lose 2 of his 12 in order to get to that neon noble gas configuration. Sodium only had to lose 1, but fluorine had to gain 1, and oxygen had to gain 2 electrons in order to reach 10. Okay? And so when we think about isoelectronic, we think about species that have the same number of electrons and therefore have the same ground state electron configuration. Okay. All right. When we talk about the ions of transition metals, this is where it can get tricky. Okay. We saw with the palladium example at the tail end of chapter 7 that transition metals, because of the energy of those D subshells, they shift around a little bit. I'm going to give you 2 generalizations, right? And so these 2 rules will help us out as we move forward to talk about ions. So these 2 rules are that there will never be transition metals whose electron configuration ends with D4 or D9. Okay. The reason for this is because, I talked about those energy levels becoming stable, lowering in energy. It turns out that two of the most stable configurations are completely filled, right? So once that subshell has all the electrons that it can possibly hold, that energy comes down a good bit. The other state that is relatively low energy is a perfectly half filled, right? Where all the orbitals have one electron and none of the orbitals have been paired up yet with more than one electron. And so if we take a look at a periodic table, if we look at chromium, so chromium has the configuration argon 4s2 3d4, at least that's what we think it should be, right? It turns out that even though the 4s subshell is full, that 3d subshell only needs one electron for it to become half filled. And so chromium really is argon 4s1 3d5. So both the 4s and the 3d are both half filled, and that's a much lower energy state for that particular element. Silver is another good one to look at. Silver is krypton 5s2 4d9. Again, it's a much more stable, lower energy configuration. If one of those electrons hops over from the 5s to give it 5s1 4d10. I don't know if you remember from chapter 2 when we talked about naming, but silver was one of those special elements that doesn't need the Roman numeral. Even though he's a transition metal, silver doesn't need a Roman numeral because silver, when he forms an ion, always forms a +1 ion. The reason that silver always forms a +1 ion is because he gets rid of that 5s electron, and then that 4d is full, and none of those electrons really want to leave. And so silver just loses the 1 ion to become silver plus. And so the general rule for electron configurations for transition metal ions is first in, first out, right? FIFO. First in, first out. So let's take a look at iron. Iron has an electron configuration of argon 4s2 3d6. 4s2 3d6. Iron forms the 3+ ion very well. And so iron 3+, we're going to lose the first electrons that we put in there. Right? When we started adding these electrons in, remember we come to the 4s subshell before we come to the 3d subshell. And so those 4s electrons are the first ones that get kicked out. But that's only 2, and so we need to take one more. So we'll take 1 from the D, and so we end up with 3d5. And so iron 3+ is argon 3d5. We lose 2 4s electrons, 1 3d. Okay. What about manganese? Manganese looks like you should be krypton 5s 2 4d4. What's manganese real configuration?
FS1, or I mean, yeah, FS1, 3 or 45.
That's right. 5s1, 4d5, right? So that both of those subshells are half full. Now, if we wanted to look at manganese, sorry, 2+, which is a fairly common ion for him, what electrons is manganese going to lose?
5s1.
Yep.
And 1 of 4d5.
That's right. So what's he going to end up as?
4d4.
4d4. Absolutely. Okay. And so that first in, first out for transition metal ions, we need to take into account both those special cases with the full and half full subshells, and then this first in, first out rule. Okay. All right. So now we've talked a little bit about ions. One of the properties that dictates a lot of these physical phenomena in elements is something called the effective nuclear charge. Okay. This, remember in chapter 2 when we talked about atomic symbols, we used Z as the charge of the nucleus, the atomic number, the number of protons. And so that's the positive charge of the nucleus. Z effective is essentially the charge felt by that by an electron, and usually we care most about that outer valence electron. Z effective has a formula for us, and it's a pretty straightforward formula. It's just Z, right? That number of protons, that atomic number, minus sigma. And so this is the atomic number. Right? Remember, that's the number of protons. Okay. Sigma, we call this a shielding constant. And for all intents and purposes in this class, that shielding constant is going to be equal to the number of core electrons. Okay. Now sigma, that sigma value, it's not really a one-for-one in terms of core electrons to shielding, but generally speaking, it's pretty close. It's pretty close. And so that's what we're going to do here for us. We're going to use that shielding constant as the number of core electrons. And so for sodium is 1s2, 2s2, 2p6, 3s1. How many core electrons does sodium have?
10.
10. That's it. All these are core, and this is valence. Sodium has 11 electrons. That means it has how many protons?
11.
11, yeah. And so the Z effective for sodium is 11 minus these 10 core electrons. So his Z effective is 1. Okay. If we go down that column, let's go to potassium. Okay. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Again, this last highest shell is our valence. Everything else is our core. What's the value of Z for potassium? Count those electrons.
19.
19. And how many of those electrons are core electrons?
18.
Yep. So Z effective for potassium also equal to 1. Right? And so this is another one of those periodic trends for that first group, those alkali metals. Their Z effective is all equal to 1. For the second group, their Z effective is all equal to 2. If we went over and we did the group with oxygen, 1s2, 2s2, 2p4. These are our valence. This is our core. Oxygen has 8 electrons. Oops, sorry, Z effective. Oxygen has 8 protons. He has 6 valence electrons. And so his Z effective is, oh, sorry, 6 valence, yeah. 2 core electrons, sorry. Number of protons minus number of core electrons gives him a Z effective of 6. And so everything in that group with oxygen is going to have a Z effective of 6. Okay. What the Z effective does is it tells us a lot about how that atom holds on to its electrons, right? The higher the Z effective, the stronger an atom holds on to its electrons. And this plays out in several physical properties. So again, the higher the Z effective, the more strongly held those electrons are by an atom. And that makes sense, right? If we think about charges as magnets, and they're not exactly, but it works for a lot of examples. If I have kind of a puny magnet and I'm holding out an electron, then it's going to be attracted. Another magnet, it's going to be attracted somewhat. But if I have a big, beefy, heavy-duty rare earth magnet and another little piece of metal, it's going to be very strongly attracted, right? And so the larger the charge that electron feels, the larger the attraction between that electron and the nucleus. And so the first thing well, as we saw, this whole group had a Z effective of 1. This whole group had a Z effective of 2. The oxygen group had a Z effective of 6. Notice that they sort of leave out the transition metals. We'll talk about why that is here in a minute, but first we're going to talk about this atomic radius. Okay. When we talk about atomic radii, it's easy enough for us to see what that is, right? That's from the nucleus out to where that last electron is. Okay. So this is the distance between the nucleus and the outermost electron. And what do we call those electrons that are in the very outermost shell?
Valence electrons.
That's it, valence electrons, right? And so we just said that the larger the Z effective, the more strongly those electrons are held. If those electrons are held strongly, do you think they're going to be closer to the nucleus or farther away from the nucleus?
Closer.
That's it, absolutely. If I hold electrons more strongly, then it's going to be closer to the nucleus. And so let me write it this way. If we have a higher Z effective, those electrons are more closely held, means we have a lower radius. Okay. The higher Z effective, the more strongly those electrons are held, the shorter that radius is. Okay. Now, but there's another factor that comes into play here, not just how strongly those electrons are held, but what shell those electrons are in, right? Remember that principal quantum number n tells us the distance from the nucleus. And so if I have, if I'm hydrogen and I have n equals 1, that electron's right next door to the nucleus. But if I'm francium and n equals 7, that electron's way far away from the nucleus, right? And so the atomic radius has something to do as well with the principal quantum number of that valence electron. So higher n value for the valence, we're going to have a larger radius. I should maybe put here shorter instead of lower. And so Z effective, we just said, increases which direction on the periodic table? Left to right, right to left. Go back a slide if you need to.
Left to right?
Yeah. So I'm going to sketch out a little periodic table here. Right. Since Z effective increases from left to right, which direction does the radius increase? Higher Z effective, shorter radius.
Right to left.
That's it. And so our atomic radius gets bigger from right to left. And so I'm going to draw an arrow. Bigger. And since larger radius, bigger radius increases with n, is the radius going to get larger top to bottom or bottom to top?
Bottom to top.
Which has the higher n? Up here at the top or down here at the bottom?
Bottom.
Yeah. And so it's going to increase from top to bottom. Right. And so helium up here, he must be our smallest. Francium down here, he must be our biggest. And so, you know, we could draw an overall arrow from small to big. That looks something like that, right? And so atomic radius increases from right to left and from top to bottom. It's all based on that Z effective and that principal quantum number.
So does that mean that the Z effective does the same thing, like increases from right to left?
So because with a higher Z effective, we actually have a shorter radius. And so Z effective, if we back up a slide, Z effective increases in the opposite direction.
Okay, okay.
But as Z effective gets bigger, it holds those electrons better, and so the radius gets smaller.
Thank you.
Sure. Okay. And so here's a little table that has those arrows again, right? Helium up here, smallest at 31. These are all in units of picometers. That's times 10 to the negative 12. And so helium here at 31 picometers, cesium down here at 265. I don't know what francium is, even though I said that was an option. Okay, so I told you that when we looked at the Z effective table, let me back up a couple slides, we didn't really say anything about these transition metals. Right? The reason we don't really say anything about the transition metals is, remember, the transition, those electrons that are going in as we go across the D block are going into the core subshells. Right? And so if we're going across from here to here, right, the 5s2 is our outermost subshell, and this 4D is really an inner shell. It's really a core subshell. And so nothing about the valence electron changes as we move from left to right across a D subshell. And so if we look here, potassium, and then this is calcium. So right here, this third one is scandium, titanium. So this is our transition metals. And the transition metals really don't change a whole lot in terms of their radius as we go across. Okay. You can see it here again too, right from here to here, our transition metals. They do change a bit, but they stay pretty constant. This one is even more apparent. From here to here, these are those inner transition metals, right? These are the F block. And then these are the D block here. Okay. The reason that those don't change a whole lot is because the Z effective does not change a whole lot across the D block. Across the D and the F blocks. The reason is, as we go from iron to copper, right, we're adding a proton, but we're also adding a core electron. Because we're adding a 3D electron and not a 4s electron, which is our valence, we're adding in a core electron and we're adding in a proton. And so Z goes up, but sigma also goes up, and they both go up by 1. And so Z effective is pretty constant across those D blocks and F blocks. Okay. So that's why we don't see much change in the atomic radius as we go across. Right. So looking at a periodic table, arrange the following atoms in order of increasing atomic radius: phosphorus, silicon, and nitrogen. Right. Remember, it increases right to left and top to bottom. So if you have a periodic table handy, phosphorus, silicon, and nitrogen. So let's take a look here. I have a periodic table where they're all labeled. Here we go. Phosphorus, silicon, and nitrogen. I'm just going to highlight those. So which of these do we think is going to be the smallest?
Nitrogen,
Nitrogen.
Nitrogen, followed by
phosphorus.
phosphorus, and then silicon the last. Yeah. So let's go back here. So we think that nitrogen is smaller than phosphorus, is smaller than silicon. Absolutely. I'm not. You won't see problems that are sort of very confusing, you know, involving transition metals necessarily, or you know, if I gave you one that were catty corner to one another, because those don't really follow our trends. One's bigger because it's further left, one's bigger because it's further down. You know, you won't be asked to equate those. And I'm not asking you to memorize those atomic radii on the previous slide either. Okay. All right. That's it for today. I will double check our Alex and make sure that this is not too far, or that Alex does not go much further than this. If Alex pushes beyond here, then I will go ahead and take down some of those topics. Okay.
Thank you.
Thank
Yep.
you.
Thank you very much. Have a
Well-
fantastic day.
You'll have
Yeah.
a good year.
You.
I wanted to review some of the slides from Friday's lecture.
Okay.
I didn't see it posted on Moodle. Will that be on there today?
Yeah, I'm sorry. I thought I had already uploaded the video, but
No, it's
Yeah.
okay.
it looks like
Thank
I
you
have.
so much. Have a good one.
Yes, sir.
Hope y'all are doing okay.
Yeah, we're doing well.